Okay, so somebody asked about that plus 0.492. In your textbook, at the end of the problem, it says the answer is negative 0.492. That's a mistake. So make sure you correct that so as you're doing the homework, you're not confused. It's a heat, I think it's a heat addition problem, so there's no way the entropy would be negative during that process. So make sure you correct that. That's due on Thursday. And these problems are not very complicated. They're actually fairly simple problems to do, but just make sure that you understand when you can apply certain criteria in situations. We're going to talk a little bit more about some entropy and temperature relations today, and as they apply in certain conditions, whether you can assume constant specific heat, whether you can assume it's isentropic, whether you can assume it's an ideal gas. So depending on what type of a process you have and what your working fluid is, then you can make certain assumptions that make the analysis a little bit easier. So just by way of review, for pure substances, the only way that the entropy in the system can change is if there is heat transfer or if there's irreversibility. So last time we defined a new term called isentropic, which means that if the process is adiabatic and reversible, then the entropy will not change. So if it's adiabatic, there's no heat transfer, and then if it's reversible, of course, there are no irreversibilities. So no friction, no head loss, nothing in the system that would reduce the work output or the work input. So a system that is isentropic will represent the best work scenario. So it'll be the maximum work output for a work-producing device and the minimum work input for a work-consuming device. So if you read a problem statement and it says that it's adiabatic and it wants you to find the maximum work output, then you automatically know that it has to be an isentropic process because it would be reversible and there would be no heat transfer. So one in which the entropy doesn't change, and again, this is just review from before that we use these approximations, one, because they're easy to analyze, but two, because it gives us the best case scenario. And it allows us to compare our real devices with these ideal scenarios where we don't have any heat losses or we don't have any irreversibilities. And again, a process that is reversible and adiabatic is always isentropic. But isentropic doesn't necessarily mean it's reversible and adiabatic, because a process can be irreversible, but if you remove heat from it, you may have a case where the entropy doesn't change, but it can still have irreversibilities and heat transfer associated with it. Okay, so this equals isentropic, but isentropic doesn't equal reversible adiabatic.
So rectangle squared.
What?
Rectangle squared.
Yes, that's a good analogy. Yeah, square is not always a square is always a rectangle, but a rectangle is not always a square. It's a good way to put it. Okay. So for no, why would it ask me that? Okay, so for entropy change of a reversible process, we don't have any entropy generation. So the simplified form of the entropy equation is just that the entropy change is equal to the integral of all the differential pieces of heat transfer at the boundary divided by the temperature. And in the case where this is isothermal, this T just comes out of the integral, and it's easy, or well, yeah, it's easy to analyze the integral when the temperature is constant. It comes right out. Just dq over T. For other processes, we need to know some functional relationship between Q and T. And so we're gonna look at a couple of different situations where we can come up with some relationships for T and entropy and other property values. So if we have a simple compressible closed system, so again, let's just talk about those terms. What is a simple system? What does that mean? When we're analyzing a simple system, all the systems we analyze in this class are simple. Well, it can be a simple system but still have mass transfer. But a simple system is one that's not complicated by gravitational effects or centrifugal effects or magnetic fields or radiation or other things that will change how these equations are analyzed. So simple systems would be like closed systems, steady flow systems, the types of devices that we've already analyzed. In this case, we're looking at a closed system, and we can say that the net change in the differential amount of heat transfer minus the net change in the differential amount of work done by the system is equal to du. So this is just the energy balance, but we've written it in differential form. And we remember now that del Q for an internally reversible system is just equal to TdS. So that's just the entropy equation that relates heat transfer and temperature. And we also have the boundary work equation, which is just PeV. So we can substitute these back in, that for some differential amount of heat transfer and some differential amount of work, we can sub in the differential amount of heat transfer with TdS and this with the boundary work and rewrite the equation. So TdS is equal to du plus PeV. And of course, if we divide through by the mass, then the u and the v and the s go to lowercase. Okay, this is known as the Gibbs equation, or the first Gibbs equation. We can also replace in this equation, we know that H is equal to U plus PV, so enthalpy is equal to internal energy plus pressure times specific volume. We can rearrange this equation and replace something. So DH is equal to DU plus PdV plus VdP. So if we take the derivative of this equation, my pointer's going out. DH is equal to DU, and then when we derive this, it's PdV plus VdP. So we have to integrate by parts. So if we okay, so this du plus PdV is dH. TdS is dH minus VdP. We haven't combined them yet. So we're replacing this du, if we take this over to the other side of the equation, with dH minus PdV plus VdP. So the minus PdV gets rid of this PdV, and then we have a minus VdP. Okay, so we take this equation and this equation, we can rewrite it in terms of this equation. Okay, feeling through the fog here. Okay, so these are both considered the Gibbs equations. They're equivalent in their application. But depending on which property values you know and which property values may be constant or not constant, like if you have a constant volume process versus a constant pressure process, you may want to use one over the other. So these relate a change in entropy to known property values: internal energy, specific volume, pressure, and temperature. So this allows us to analyze any system that's a simple compressible system undergoing some sort of change, whether it's reversible or irreversible. If we know certain property values, we can calculate the entropy change. Or if we know the entropy change, we can calculate other property values. So this is just another tool in our arsenal in evaluating these systems that allows us to consider what irreversibilities are doing to our system and how we can make it better, how we can improve. So if we find that there's a huge pressure drop and that's contributing to the change in entropy, then we may need to change something about our system and minimize the pressure drop. Of course, analyzing the other pieces, the other equations, the energy balance, mass balance, etc., we can see whether the trade-offs that we make in kind of playing around with these property values are worth it or not financially for our system. Getting more specific, if we have liquids and solids, generally they can be assumed to be incompressible. And what does incompressible mean?
The volume does not change.
Okay, the volume doesn't change, or the density doesn't change. The specific volume, the total volume, may change. But it's the specific volume, which is the volume divided by the mass, or the reciprocal of density. So if this term dV is 0, then our first Gibbs equation reduces to this. So we have ds equals du over t plus pdv. So if this dv is 0, then it's du over t. And we can rewrite this because du is equal to the specific heat times the change in temperature. We can substitute that in here. So we can approximate the entropy change of any liquid or solid, assuming it's incompressible and has constant specific heat, as the change in entropy is equal to the integral of this, which is approximated as the specific heat times the integral of this dt over t. So if we integrate that, we get natural log of T2 over T1. Okay, so again, this is another tool. It's used only in specific cases where we have a liquid or a solid to analyze the entropy change. So if we know the initial and the final temperature, and we have some tabulated value or set of values for any given substance, then it's fairly easy to calculate the entropy change. And if a substance is truly incompressible, then it only depends on temperature. So we don't have to worry about anything else. And if it's an isentropic process, then this integral is equal to 0. So S2 minus S1, since S2 equals S1, that will be 0, that side of the equation. And how do we get the natural log of something equal to 0? Well, C can't be 0. The specific heat can't be 0. So T2 must be equal to T1 because the natural log of 1 is 0. So in order for a process to be isentropic for a liquid or a solid, it would also have to be isothermal, which means really not very much is happening in this process. Okay, because there's no heat transfer. Okay, so for an incompressible substance, then it has to be an isothermal process as well. So if it's adiabatic and reversible, there's no heat transfer, there's not a lot going on for isentropic processes for liquid and solid. But if you know it's isentropic, then you can determine that it's isothermal. Okay, so let's just do an example. In this case, we're using liquid methane. And methane, when it is not a liquid, can be considered an ideal gas. But when it is a liquid, it's not an ideal gas. So we want to determine the entropy change for liquid methane as it undergoes a process from 110 Kelvin and 1 megapascal to 120 Kelvin and 5 megapascal. And we're going to do it two different ways. First, we're going to use the tabulated property values. So we'll just look up the properties from the table. And this is, I think this table is just in chapter 7. It's not in the back of the book. And then the other way is to approximate it as an incompressible substance. So we're just going to look and see how much error is involved in doing that. So if somebody wants to look at that table and determine what is S1 and what is S2, what are my values? So at 110 Kelvin and 1 megapascal, what is S1? 4.875. Okay, 4.875 is S1. And what's S2? 5.145. This is kilojoules per kilogram Kelvin. Are we given a mass in this problem? No. Okay, so delta S is just S2 minus S1, and we calculate that simply 0.27 kilojoules per kilogram Kelvin. Okay, so let's use the alternate method. If we assume that S2 minus S1 now is equal to C average times natural log of T2 over T1. Okay, what do we use for our average C?
You take the C values at each temperature and you use the average of those.
Okay, so what's our C value at 110 Kelvin? And
3.47.
okay, so 3.471 plus what's our other C value?
3.486.
3.486 divided by 2 gives us 3.4785 kilojoules per kilogram Kelvin. Okay, so we can plug that in. C average 3.4785 I'm going to call it, natural log of T2, and it's very important when you're using temperature, of course, to keep it in Kelvin. It's already given to us that way. T2 is what? 120. And T1 is 110. So what is this change in entropy? 0.303 kilojoules per kilogram Kelvin. Okay, so compared to what we had before, if we calculate the percent error, just the absolute value of 0.303 minus 0.27 divided by 0.27 times 100 is 12.22%. Okay, so 12%, depending on what precision is required, this could be acceptable, maybe a little bit higher than we would want to see, but it's a good back-of-the-envelope calculation just to determine your entropy change in the absence of information from the tables. Okay, are there any questions on this example? It's pretty straightforward, again, using property tables versus using equations. We've done this before in chapter 6, I believe it was. Okay, now we have some more special scenarios. So now we can look at what tools are available to us for ideal gases. So from the first Gibbs equation, we just take T, we have TdS is equal to du plus PdV, so we just divide through by T, we get du over T plus PdV over T. Now for an ideal gas, what else do we have at our disposal? What's an additional equation that we can use? Okay, PV equals RT, or PV equals MRT, or PV equals nRT, depending on which form you're using. So P is equal to RT over V. We can plug that into this equation for P right here. So we have RT over V, dV over T. And for du, we can substitute in C sub V dt. So if we plug this into the equation ds here, and we take this integral, we have the integral of C sub V dt over T plus R natural log of V2 over V1. So if we integrate this with respect to dV, then we get this out of the equation. Okay, so this is an additional equation we have in terms of ideal gas. We can also take the second Gibbs equation and do some similar magic. This time we're solving for V in terms of P. We can substitute that into the equation there, and we get, again, this integral C sub P dt over T, and then minus R natural log of P2 over P1. Okay, this is the exact approach. If we can assume that C sub P isn't a function of T, and that it's just some constant average value, we can move it outside of the integral, integrate this part of it, and have natural log of P2 over T1, similar to what we did before. We do that. Okay, so again, if we want to make that approximation where C sub V is some constant average value that we're not saying it's a function of T, that it's linear with T, we can take it outside the equation, just find the average of it, and then integrate this piece of it. So now we have, for the first Gibbs equation, this relationship, and for the second Gibbs equation, this relationship. Okay. So we have these two equations, and as previously mentioned, you may want to use one versus the other. So in which case would you want to use this equation?
You're given the top.
Okay, if you knew the initial and final volume, or you knew the initial and final, and you knew the initial and final temperature. You don't have volume information, but you have pressure information, then you can use the second Gibbs equation. So there's two different versions of the same idea. They're just in terms of different property values. So depending on what you can measure or what is given to you in the problem statement, or in real life, what you have available in terms of information, you might use one versus the other. And again, this is just how we calculate the constant average specific heat. It's just at the average temperature, or as the average of the two C sub P's, and that value is generally pretty close to one another. Okay, so this was the approximate analysis. So we've taken this outside the equation. We've assumed that it's some average value. Let's look now at the exact analysis for an ideal gas. The relationship for specific heat and temperature is known. There's some functional relationship for it, and it has been tabulated using absolute zero as reference. So this value here, this is not entropy really. It's the reference entropy, so S superscript 0, is equal to this equation. So at whatever temperature you look up this S superscript 0, it's equal to the integral from 0 to that temperature of this part of the equation. So the specific heat times dT over T. Okay? If you have S2 minus S1, or S superscript 02 minus S superscript 01, okay, so we just said we're going from 0 to temperature 1 and from 0 to temperature 2. So this goes 0 to temperature 2, this will go 0 to temperature 1. If we combine those two together in one integral, from 0 to 1 disappears, so we have from 1 to 2 the integral of c sub t as a function of t, dt over t. Okay, so these terms right here, this S superscript 0 is a function of temperature only. It's not reliant on pressure. Okay, similar to how internal energy and enthalpy for an ideal gas are a function of temperature only. But entropy is a function of temperature and pressure. So if we want to calculate the actual entropy now, what we have, S2 minus S1, for an ideal gas only, is equal to this reference entropy 2 minus the reference entropy 1 minus this factor here, which sort of corrects for pressure. Okay? So all we've done, or all we will do, is we will use these tabulated values of how the specific heat varies with temperature for a given substance. We have this value already tabulated, and we can use it to calculate what our actual entropy is if we know the pressure. Okay. So if we look at our tables in the back of the book, we look at table A17, is the one for air, I believe. Okay, so you'll see the ideal gas properties of air. We have the temperature in Kelvin, enthalpy, which is a function of temperature only, this reference pressure, which we'll get to later, internal energy, and then this S superscript 0. Okay, so that is our reference entropy that's a function of temperature only, and it's calculated using the specific heat as it varies with temperature, which is a known formula, but because it's complicated and we don't want to have to calculate it every time, it's been tabulated for us, and we can use this relationship substituting into this equation here. Okay. So now we can use our tables for all of the analysis that we want to do on these entropy problems for what? Ideal gases only. Okay, all of these assumptions that we've made in this section, we talked first about the assumptions we make for incompressible substances, or liquids and solids. Now these are only specific for ideal gases. You can't apply them to water or R134A or any of the other substances, only for ideal gases. So let's do a problem that illustrates how to use these tables. We have an insulated piston cylinder device containing 300 liters of air at 120 kilopascals and 70 Celsius. The air is now heated for 15 minutes by a 200-watt resistance heater placed inside the cylinder. Determine the entropy change of air, assuming first, constant specific heats, and second, variable specific heats. Okay, so those are the two examples that we've just, or the two different sets of equations that we've just discussed. Okay, so some of the assumptions that we can make, it's an ideal gas. It's constant specific heat in the first case, or in part A, and then variable specific heat in the second case. Okay, so when we assume constant specific heat, that's an approximate approach, okay, because we're approximating that the specific heat value is is some constant value. When we say that it varies, that's another way of saying we're going to use the exact approach to determine the actual entropy change. Okay, so how should we start this problem? What kinds of information do we have? What information might we need? How do we do this?
Well, first, we have to use the ideal gas entropy change, that whole piece.
Okay, so in part A, we use this equation. So delta S for the system is equal to M times S2 minus S1, which is equal to M times C sub P average, natural log of T2 over T1, minus R, natural log of P2 over P1. And this M is multiplied by everything. So our average C sub P, natural log of T2 over T1, minus R, natural log of P2 over P1.
And then we need to solve for the final, well, we know the pressure is going to be set.
Okay, so what do we know in this problem? Do we know the mass? Okay, we don't know it explicitly, but we could probably find it out using the ideal gas law. Do we know the two temperatures?
We can find T2.
Okay, we don't know T2. We do know T1. And we know the pressures. Okay, the pressure is constant. So this is going to be natural log of 1. What does that mean? 0. Okay, and we can look up R in the table. Okay, so let's find the mass. So M is equal to P1 V1 over R T1. So it's 120 kilopascals times 0.3 meters cubed. So I've already converted liters to meters cubed. R is 0.2870 kilopascals times meters cubed per kilogram Kelvin. And then our T1 is 17 Celsius, but we need to convert that to Kelvin. So it's 290 Kelvin. So our mass is 0.4325 kilograms. How do we find T2?
I think if you just set them equal, we don't know the final line.
What other information are we given in this problem? Or what other tools do we have in our handbag for these types of problems?
Energy equation and just take the work input.
Okay, so let's use the energy equation. So Q in minus Q out plus work in minus work out is equal to M times what for a closed system? Don't skip. U2 minus U1. Okay, for a closed system, we don't have to consider the flow, so it's internal energy and not enthalpy. Do we have any heat transfer? Nope, it said in the beginning it's an insulated piston cylinder device. Do we have work in?
Yeah.
Okay, what is our work in? Electrical work. Do we have work out?
Boundary work.
Boundary work. Don't forget the boundary work. Okay, so we have work electrical minus the boundary work is equal to M times U2 minus U1. We can combine these terms. The boundary work is equal to PdV. It's a constant pressure problem. So our electrical work is equal to M times H2 minus H1. So we can solve, well, we can rewrite this also as C sub P times T2 minus T1. So we can solve for T2 is equal to T1 plus this electrical work divided by the mass times C sub P. So it's 290 Kelvin plus our electrical work is 200 watts, so 0.2 kilowatts times 15 minutes times 60 seconds per minute to get kilojoules divided by M, we calculated 0.4325 kilograms. And C sub P, what do we use for C sub P? We're assuming a constant average specific heat, but we don't know the final temperature. Luckily for you, I know the final temperature, so I'm going to assume that our constant average specific heat is evaluated at 450 Kelvin.
Why would we do that? You could just write C sub P as a function of T2 though.
But I need to solve this equation.
So you can still
So if you don't know the final temperature, you can make an educated guess as to what the final temperature might be, so you can calculate an average C sub P. In this case, I'm going to guess the final temperature is somewhere around, I don't know, 700 Kelvin.
for us not knowing that.
If you don't know it, you assume a final value, you calculate the final value, and you see how close you are. If you're pretty close, then you know that you've assumed a pretty good final value. If you're not close, you're way off to what you have assumed, then you need to adjust your assumption and iterate and go through the process again. Okay. So if T2 is unknown, you have to make a guess. We're making a very educated guess in this case because we already know the final value. So assume C sub P evaluated at 450 Kelvin. So that would be like the average temperature at the end of the problem. And that value is 1.02 kilojoules per kilogram Kelvin. Okay, so if we solve this, we find out that T2 is 698 Kelvin. Okay, so we say, all right, our assumption was pretty good, fortunately for us. So that's fine. If our assumption was way far off, then we might have to iterate and do it again and see how much our answer changes. Okay. So what are we doing this for? Okay. So we got to plug T2 back into this original equation. I'm going to stay over here. So now we know T2, we know T1, we know C sub P average, we assumed the correct value, we've calculated the mass. We know P2 is equal to P1, so this whole term goes to 0. So if we just put in the terms for this, we calculate delta S is 0.387 kilojoules per Kelvin. Okay, so again, this is the approximation because we're assuming constant average specific heats. So we're approximating our entropy value. Now let's do the exact analysis where we allow C sub P to vary and we use the table in the back of our book. Okay, so in this case, we still do our energy balance, so Q in minus Q out, et cetera, et cetera. We find that our work electrical in is equal to times H2 minus H1. Okay, so we've done everything the same up to this step, but instead of making our approximation that this is equal to C sub P times T2 minus T1, we're going to solve for H2. So we say H2 is equal to H1 plus this electrical work in divided by the mass. H1, we look up in the tables. So for an ideal gas, it's a function of temperature only. We can look up the H1 value is 290.16 kilojoules per kilogram. This is the same as what we did before, plus
The H1 is not money mass.
no, because this moves over here, divided by and then H. The same thing we did. 200 watts, so 0.2 kilowatt times 15 minutes, 60 seconds per minute. Divided by the mass, so we found that to be 0.4325 kilograms. H2 is equal to 706.34 kilojoules per kilogram. So if we look in our table, so let's go to table A17 for air. We want to find where H is equal to 706.34 kilojoules per kilogram. So if you look in here, it's somewhere between 690 and 700 Kelvin. At this point, the temperature is not what we're looking for. We're looking for S superscript 0, or the reference entropy. So if we look there, we can interpolate using the known value for enthalpy to find our reference entropy value. So S2 superscript 0 is equal to 2.5628 kilojoules per kilogram Kelvin. Okay, so that's S2. Up here, when we went to look up H1, we can also look up S1 superscript 0. We find that value to be 1.66802 kilojoules per kilogram Kelvin. Okay, now we have these two known values. We can plug those into our equation. So the change in entropy for a system using the exact approach is equal to the mass times S2 minus S1 superscript 0 plus R natural log of P2 over P1. And again, because P2 and P1 are equal, this goes to 0. So all we have is M times S2 minus S1, which if we plug in the numbers for that, we get 0.387 kilojoules per Kelvin. So we compare that to the value that we calculated using the constant average specific heat, and it's exactly the same. One of the reasons that it's the same is because the pressure in this problem is the same. It doesn't vary. So when you have wide pressure variations, then this approximate approach differs more widely from the exact approach, given the same temperature interval. And then, of course, as your temperature interval increases, then it becomes less and less accurate because the specific heat is not necessarily linear over a large temperature interval. And when we calculate the average specific heat, we're assuming that it's a linear relationship. Okay, so are there any questions on this problem or how to look up our reference entropies? Okay, it's very important that when you go to these tables that you understand the S superscript 0 is not the entropy at that temperature necessarily. It's the entropy, reference entropy at that temperature, but as your pressure varies, then you'll have some change in entropy due to the pressure variation as well. Because entropy is a function of temperature and pressure. Okay, some additional equations that we can derive using the Gibbs equations and some clever manipulation and the eigengas law, I should say. All of those together that we can make some manipulations, and if you're interested in how these come about, it's on page 357 in your textbook. Okay, so when the entropy is equal to 0, so the change in entropy is equal to 0, that means S2 minus S1 is equal to 0. So we can set one aside of that equation equal to 0. So then we have C sub B natural log of T2 over T1 plus R natural log of P2 over P1 is equal to 0. Rearrange, natural log of T2 over T1 is equal to R over C sub B, natural log, and this time I'm going to flip these because I just got rid of the negative sign, P1 over P2. No, Well, this is for one of the given equations. The relationship between R and C sub P and C sub V. So C sub P minus C sub V is equal to R. And then there's also a term called K, which is equal to C sub P over C sub V. So R over C sub V is equal to C sub P over C sub V minus 1, or K minus 1. And this actually, I'm going to change that to these. Sorry.
Is there supposed to be a negative somewhere?
Okay, I'll do one additional step. So this is negative V2 over V1. Or I can factor the negative through, and natural log of V2 over V1 is equal to the negative natural log of V1 over V2 to get rid of the negative sign. So I skipped a step, but okay. So with the V's in there, so this side of the equation, we can take this exponent up. So we have natural log, this times natural log of this is equal to natural log of V1 over V2 R over C sub V. And this we said was equal to K minus 1. So the natural log of T2 over T1. So then T2 over T1 is equal to V1 over V2 to the K minus 1. Okay, so it's just manipulations using the rules of natural log to kind of, and the knowledge of these relationships, to put it into a form that allows you to easily analyze how the change in temperature affects the change in specific volume, or what the relationship is there. Again, this approximation only works when you have an ideal gas and it's isentropic. So the process has 0 entropy change. So we've set that side of the equation equal to 0. We can separate and manipulate and then come up with these isentropic entropy, isentropic ideal gas relationships. Okay, so these are very useful when we're dealing with isentropic problems, because if we know the initial temperature and maybe the final temperature and volume, then it's easy to calculate whatever is unknown. So you have to know at least 3 of these values in order to determine the 4th, but in many cases we do know those in our problem. So let's just do an example where we use this knowledge. Air is compressed in an isentropic compressor from 15 psi of 70 Fahrenheit to 200 psi. Determine the outlet temperature and the work consumed by this compressor. So which of those relations do you think we should use? Which one would be useful to us?
The TP equals, TP, the minus K over K.
Okay, so T2 over T1 is equal to P2 over P1 to the K minus 1 over K. Okay, so why did we select this one? Because we know P1, T1, and P2.
Isn't it P1 over P2 or P2 over P1?
P2 over P1. Yeah, it's the middle one. Okay, so T2 over T1 equals P2 over P1 to the K minus 1 over K. So for air, we can look up in the tables. K is equal to 1.389 K. So T2 is equal to T1 times P2 over P1 to the K minus 1 over K. We plug in the numbers for that. T1, we need to convert it to Rankine, so 70 plus 460 Rankine. P2 is in PSIA, so 200 PSIA over 15 PSIA to the 0.389 over 1.389. So we calculate this to be 1095 Rankine. Okay, so we've determined the outlet temperature. What's the second piece of this problem? What do we need to do?
Work consumed.
Work consumed. So if we want to find the work, what equation should we use? Energy out. Okay, so Q in minus Q out plus work in minus work out is equal to m dot times H2 minus H1 for a single inlet and outlet. Okay, so this problem, they tell us it's isentropic. And we can't really assume that isentropic means adiabatic and reversible, but we're given no other information about irreversibility or whether or not there's heat transfer. So it's a safe assumption that this compressor is isentropic because it's adiabatic and reversible. So we're going to assume there's no heat transfer. If they had given us some information about heat transfer, then we would know that it was irreversible, but that the irreversibilities matched up with the heat transfer change in entropy. Okay, so adiabatic, Q in, no Q out. We don't have any work out because it's a compressor. We're putting work into the system. So work in is equal to m dot times H2 minus H1. We're also not given a flow rate in this problem. So if we divide through by m dot, then we have a lowercase w is equal to H2 minus H1. And again, we're using the approximate approach, so this is equal to C sub P times T2 minus T1. So if we look up C sub P, it's 0.245 BTUs per pound mass Rankine. T2 is 1095 Rankine, and T1 was 530. So we find 138 BTUs per pound mass. So that's how much work we have to put into the system if it was an isentropic compressor. If it were an actual compressor, would our work input be greater than or less than this number? Greater than. We'd have to put more work into the system because there would be irreversibilities that we had to overcome and likely heat losses. Okay, so now let's talk about the exact analysis. It's pretty straightforward. If we set the other side of the equation equal to 0, then we just have this S reference entropy at state 2 is equal to the reference entropy at state 1 plus R natural log of P2 over P1. So there's not all these fun little tricky equations that we had for the first case. It's pretty simple and straightforward. We just have to use the tables in order to look up the reference entropies. And if we know the initial and final pressure, then it's fairly easy to do that. We do have something called a relative pressure, and this is different than what we did for liquids and saturated liquid vapor mixtures, where we calculated it based on the critical point, because ideal gases are so well above the critical point, but this is a different kind of reference pressure. But if we have the ideal gas equation, and we take the exponential of it, so we take the exponential of this side, so if it's P2 over P1, we move this R over here, so we have S1 minus S2 over R. Rearrange that negative. How did that turn into plus? Yeah, that's right. Okay. So just rearranging and taking the exponent. Sorry, I'm a little slow today. of each side, then we come up with this relationship where we deem this term here, this S superscript 0 over R, we're going to now call the relative pressure.
EXP?
The exponent.
The exponent.
It's like the inverse of the natural log.
Okay. Inverse of the natural.
Yeah. So the exponent,
We just heat it over.
Where you would usually see it.
exponent of the natural log of something is equal to something. It's like how you get rid of the natural log.
Letter E raised to the power.
Okay.
Yeah.
I do that.
X. Okay. So this term here, we are now calling some relative pressure. It's unitless, and we can rewrite the above equation as such. So again, we have some property value that's dependent on temperature only, and if we know this respective pressure ratio, which we use later when we get into IC engines, the very last section that we talk about, if we know this pressure ratio, then it will help us determine our actual pressure ratio. Okay. So again, these are tabulated in table 817. So if you look in there, you can see this piece of R is a value. And again, this is another way, if we didn't know the final pressure, then if we knew the initial pressure and we could look up this PR1 on the table, and then find a final enthalpy, then we could use the final enthalpy to look up this piece of R2, and then we could back out the pressure from that. So it's another tool we have available to us. And sometimes instead of a pressure ratio, we're given a volume ratio, and this V sub R is also tabulated there. So this V is just equal to T over P there. So it's just another equation, again, that allows us to analyze our system given certain unknowns or certain knowns and unknowns to allow us to find the final state. And depending on what the end game is in your problem, whether you're trying to determine the work input or output, or trying to determine the final temperature, or so on and so forth, different equations may be more useful to you than the other. And it's important to note that this ratio of the T2 over PR2 divided by T1 over PR1, this ratio is equal to the ratio of these reduced specific volumes, but this T2 over PR2 does not equal VR2. It's just the ratio of this is equal to the ratio of this, but there's not a direct correlation between the T over the reduced pressure is equal to V. That's not true. So let's do a problem utilizing some of this. Air is compressed in a piston cylinder device from 90 kilopascals and 22 Celsius to 900 kilopascals in a reversible adiabatic manner process. Okay, so reversible adiabatic, what does that mean? Isentropic, so it's constant entropy. Determine the final temperature and the work done during the process first, assuming constant specific heat, and second, using variable specific heat for air. Okay, so this is an ideal gas. We have certain tools available to us that we don't for any other process and type of working fluid. So we can't do this for solids and liquids, but for an ideal gas we can. Okay. So what information do we already have, and what information might we need, and how do we get it?
PV equals RT.
Okay, PV equals RT. But because this is an isentropic process, we can jump straight to these other equations. So T2 over T1 is equal to P2 over P1 to the K minus 1 over K. So we can directly solve for T2 is T1, P2 over P1 to the K minus 1 over K. For air, K is equal to 1.393 know our initial final pressure and our initial temperature. So this is 295 Kelvin. Again, you have to use Kelvin. 900 divided by 90 kilopascals to the 0.393 over 1.393. So this gives us a final temperature of 564.9 Kelvin. So then we can use this final temperature and the initial temperature to come up with some average temperature at which we can evaluate our specific heat. So 295 plus 565 over 2, T average is approximately 430 Kelvin. So we can look up our property values already given to us in the table at 425 Kelvin. So we can either interpolate at 430 or just use 425 because it's close enough that the values don't change when you interpolate very much. Okay, so C sub V is .730 kilojoules per kilogram Kelvin. We're going to need that later. Okay, so we're still doing part A, constant average specific heats. We've determined the final temperature. How do we determine the work done during the process? What equation do we need to use? Energy balance of Q in minus Q out plus work in minus work out is equal to M times what? U2 minus U1. Okay, it's a closed system. We don't have to worry about the flow work, so it's internal energy instead of enthalpy. We're told it's adiabatic process, so there's no Q in or out. And do we have work in or work out?
Work in.
Work in, so we're doing work on our system. Work out goes to 0. Work in is equal to M times U2 minus U1. We don't know M, so we divide through by the mass, and we have our lowercase w is equal to C sub V times T2 minus T1. So we plug in the numbers for that, 0.730 kilojoules per kilogram times Kelvin, multiplied by T2, 564.9 minus T1, which was 295 Kelvin. So we find our work to be 197.0 kilojoules per kilogram. Okay, so this is part A. Using the approximate analysis where we assume that the specific heat varies, but it varies linearly, so we can take just some constant average value in the middle. Okay, the second method for an isentropic process now is we can either use our reduced pressures or our reference entropies to find our final values. Okay, so again, T1 is 295. So if we look in the table, PR1 is 1.3068, and U1 is 210.49 kilojoules per kilogram. That's table A17 for air. Now we can use our pressure ratio relationship. So PR2 over PR1 is equal to P2 over P1. So PR2 is equal to PR1 times P2 over P1. So that's 1.3068 times this pressure ratio, 900 divided by 90 kilopascals. We find 13.068. So then we go back to the table and we say, okay, at what point do we have a pressure ratio or reduced pressure equal to 13.068? So we look on here, it's somewhere between 560 and 570 Kelvin in the temperature. So we can interpolate to find our final temperature T2 is equal to 564.9 Kelvin. And then our final internal energy, we can also interpolate to find is 408.09 kilojoules per kilogram. So now if we were to perform the energy balance again, we would find that W, lowercase w, is equal to U2 minus U1. So if we plug in the numbers for that, we found U2 by interpolation, U1 we just looked up directly on the table. It's 408.09 minus 210.49 kilojoules per kilogram gives us 197.6 kilojoules per kilogram. Okay, so the difference in those two cases, here we calculated it to be 197 using the approximate approach. There we looked it up directly from the tables. We found it's 197.6 kilojoules per kilogram. So it's pretty close. Very low percent error in that case. Okay, so it's important to understand, number one, in which cases you can apply different types of equations. So if it's a liquid or a solid, meaning it's an incompressible substance, then you can use a certain set of equations. If it's an ideal gas, you can use another set of equations. If it's isentropic ideal gas, then there's an additional set of equations that you can use. So you have to make sure before you just start applying equations to your problems that you know in actuality what assumptions you can make, which ones are applicable in your case, and then start applying the equations. And again, the difference between the exact approach and the approximate approach. So if you understand that when you let C sub p vary linearly and you take the average, that you're making an approximation. So that's the approximate approach. And then when you're using the tabulated reference values, that's the exact approach.
So you're going to tell us which one we have to use?
Well, in all the homework, they specifically say which one to use, but yeah, I most likely would say which one I wanted to use. Or if I were to say by the most accurate method, which one would that be? Okay, the exact approach. And if I say things like, I want the minimum case or the maximum case, what does that mean?
It's the theoretical limits.
Okay, the theoretical limit, so it's the isentropic case. So anytime in a problem when it says the maximum work output or the minimum work input, you can assume they want the reversible case, and if it's a reversible problem that's also adiabatic, then it's isentropic. Okay, so they don't always tell you this is an isentropic problem. You have to look for those keywords in your homework as you do it.
Will there be a keyword close enough for government?
That phrase is overused.